Welcome back to the online Causal Inference seminar. Today, we are pleased to have Anish Agarwal from MIT and Shen from Berkeley, who will be talking to us about synthetic interventions. Our discussion today will be Jason Poulos from Harvard. Questions today will be handled by Dominic, so now I'm switching over to him.
Thank you, Georgia. Yeah, as usual, please submit your questions via Q&A. Some of them will be selected to be answered live. If you are selected, please raise your hand. And if you participate, please keep in mind that the talk will be recorded. Yeah, thank you all for coming. And now with that, we switch over to our speaker.
All right. Is my screen seeable? All good? All right. So good morning, everyone. My name is Anish Agarwal. I'm a fifth-year PhD student at MIT. I'm advised by Professor Alberto Abadi, who is in MIT Economics, Munzer Dale and Devavat Shah, who are in MIT EECS. Today, me and Dennis will be presenting our work, Synthetic Interventions. It's a joint work with Devavat Shah and Dennis Shen, who are also panelists on this talk. So thank you very much for having us. And I'd just like to say a special thank you to the organizers of the seminar. It's been wonderful to attend. And Michael in particular for helping organize with me. So the talk outline will be in 5 steps. We will first begin with a motivating example from COVID-19 that will motivate the synthetic interventions framework and the estimator. After that, I'll actually present the synthetic interventions estimator. After that, I'll present a causal framework for when and why SI, which I'll call in short for synthetic interventions when it works. And then I'll hand it off to Dennis. We'll go through some of the key theoretical results we have and an interesting application of synthetic interventions, which is synthetic A/B testing. So let's begin with the COVID-19 motivating example. So here we have a plot of the US. On the y-axis is the number of COVID-19 related deaths that happened in America. On the x-axis is the day since 80th deaths. So 0 represents the day that America went through its 80th death. And many epidemiologists consider this the start of a COVID-19 breakout in any country. So as you can see that before day 0, the number of COVID-19 deaths was relatively flat. And after day 0, there was this exponential rise in the number of COVID-19 deaths that happened in the US. I think everyone agrees that there was a tragic event that happened in the US, which was the number of deaths that happened from COVID-19. I think what there's less agreement upon is what we could have done. So some people say, well, if we had really locked down the country, then we could have avoided a lot of COVID-19 deaths that happened needlessly. Other people say, well, if you shut down the economy, all that would have happened is it led to more economic hardship and would have made really little difference to the number of COVID-19 deaths we had. And so part of the question is there a way for us to think about the health and economic trade-offs associated with COVID-19, and is there a framework to do so? So that's going to be the motivating example that we use for the next few slides. Now you can look at what happened across the globe. And once COVID-19 started, different countries did very different things. So here on the left is a plot that we pulled from publicly available data from Google. So they're the Google mobility reports. So the y-axis represents the average reduction in mobility from January of 2020, which was when there was really no COVID-19 in most countries. And the x-axis is a variety of countries. So you can see countries like the US, UK, Spain, where COVID-19 is particularly bad when it just started. There was almost no reduction in mobility pre and post COVID-19 breakout. And there were other countries such as Germany and Brazil, there was a moderate drop in mobility, what we call a 5 to 35% reduction in mobility. And there were countries where there was a significant drop in mobility, such as India or Denmark, etc. So there's a natural cluster, at least roughly speaking, in the 3 kinds of countries: ones that are a small reduction in mobility, a moderate one, and a severe reduction in mobility, from less than 5 to 35, and greater than 35. And so one natural question that you could ask is, what would have happened to the US, say through appropriate policy, if it had gone through a low mobility restriction? Well, this is actually what happened in reality. A moderate mobility restriction, which is a 5 to 35% reduction, or a high mobility restriction, which is, and the metric of interest is the number of COVID-19 related deaths that would have happened in the country. So the bottom 2, which is the moderate and high, are counterfactual USs that we want to ask this question about. So as I know is familiar to probably most people here, is the potential outcomes framework. So this is one way of thinking about this question, or posing this question. And the potential outcome framework basically posits that a country contains many latent cells. So there's a version of the US under a low mobility restriction, a version of the US under a moderate one, and a version of the US under a high one. As we know, a fundamental problem of causal inference is that we can only observe the US under one of these policies, but we want to know all possible outcomes. Now, one way of representing all the data that we care about is through what we call a potential outcomes tensor. So a tensor is nothing but a higher dimensional matrix. So matrix can be considered an order 2 tensor, which has rows and columns. And here what we're presenting is an order 3 tensor. So you have rows here representing countries, columns representing time, and the third dimension, which we call slices of this tensor, represent different interventions. So you can see that the arrow here represents the US's mortality rate on day T under the low mobility restriction. Now the second arrow here, we're keeping the US fixed and we're keeping time fixed. And this particular entry of this tensor represents US's mortality rate on day T under the moderate mobility restriction. And similarly, the US's mortality rate under the high mobility restriction. Now, if we had access to this entire tensor, we'd be done. We could answer any of the causal inference questions that might be of interest, such as the US's mortality rate under all the various interventions. Now, the problem, of course, is that we don't actually get to observe that potential outcomes tensor. What we observe is a very sparse version of this tensor. So here, white represents missing entries. And as we see, you can see this from the Google mobility reports, that pre-COVID-19 breaking out, all countries had basically done nothing. And they were all under the low mobility restriction. So you see that pre-COVID-19, we observed the gray slice for all countries and the moderate and high slice of the missing. Now, once COVID-19 broke out in these various countries, different countries did different things, as we saw. So there's some countries that remained under low, some countries that were under moderate, which are represented by blue, and some countries represented by green, but which went under high. So for a country like the US that remained under low, we do not get its observations under moderate and high. Hence, the first row, for example, is missing. Similarly, for countries that were under the blue intervention in post-COVID-19 breakout, we're missing their data from low and high, and so on. Right, so what we want to recover is this whole tensor, but we only get the sparse version of it. And in some sense, what we have seen is that a lot of problems in causal inference can really be rewritten as a problem in tensor completion. So say our goal was to do policy evaluation, was to see what the effect of these different mobility restrictions were. Well, we can observe these outcomes, which can be represented through this sparse tensor. And then you can ask a question like, say, what would have happened to the US have it enacted the high mobility restriction? And that can, if we had access to these missing entries, which is represented by the shaded green in the top right image, if we had access to the data, then we could answer that question. And in some sense, people always say that causal inference is a missing data problem. And in computer science, one of the hottest fields is tensor completion. And they also say that tensor completion is a missing data problem. And I think there's a deep relationship between these two fields in terms of the types of goals you can solve. And a lot of the terms you have in causal inference have an analogous term in tensor completion. For example, the notion of confounding in causal inference can be thought of in tensor completion as simply missing not random data. And different observational experimental studies basically lead to different sparsity patterns in your observed outcomes in your tensor completion. And then the goal in causal inference is to estimate counterfactual potential outcomes. And in tensor completion, you can write that as simply imputing specific missing entries. So you can see there's this kind of one-to-one mapping between problems in tensor completion and causal inference, at least for discrete settings. So now to actually go back to our goal. So the goal is to learn n times d causal parameters. So here n represents n units that you have, for example, n countries. And d represents the various interventions you have. So in the COVID-19 example, d equals to 3 because you have low, moderate, and high. And each entry of this matrix represents some causal parameter of interest. For example, what's being pointed to by the arrow is the average post-intervention outcome of unit n under intervention d. Now the question is, can we learn all these n times d parameters despite observations that are far less than n times d? And second, can we be able to do this despite unobserved confounding, which means that you're missing not random data? So that's going to be the goal of this work. And kind of the key punchline of the synthetic interventions estimator is that you can learn these n times d causal parameters despite having access to simply n times 2 observations. The key data requirement is that we need to observe all the various units, n units, under one intervention that they're that's common. For example, in the COVID-19 example, this would be the pre-intervention period where they're all under the low mobility restriction. But this is more general. It could be just any intervention for which we observe all the various units. And we can call that control, for example. So that's the goal of the work. And the key takeaway is that synthetic interventions lets you do this with n times 2 observations. So now I'm going to just show you the results of applying synthetic interventions on the COVID-19 data. And afterwards, I'll show you the estimator. A major credit for running the simulation goes to Abdullah Alomar, who was a master student in Devavrat's group at MIT and is about to start his PhD in EECS as well with Devavrat. So just to recall, this is how the data for the US looked like pre and post COVID-19 breaking out. Now, using the synthetic interventions estimator, we produce these 3 synthetic trajectories. So the dotted gray line is the synthetic US under low, the dotted blue line is the synthetic US under moderate, and the dotted green line is the synthetic US under green, is under the high mobility restriction. And what we did is we held out the US's data up post-COVID. So we held out the solid gray line post day 0, and we saw whether we could recreate it using the dotted gray line. And as desired, the dotted gray line and the solid gray line are close to each other. So that serves as some validation that the synthetic interventions estimator is doing something reasonable. And then the other 2 lines, the dotted blue and dotted green, are counterfactuals. And if you believe the estimates of the synthetic interventions estimator, then you can see that from synthetic low US to the moderate US, there's a sharp drop in the number of COVID-19 deaths. And the marginal gain from the moderate US to the high US is relatively small, which is an interesting takeaway if you believe these estimates. We recreated these results with all the different countries within the Google mobility dataset. Here's another one for the UK, which was under a low mobility restriction. And again, the solid gray line and the dotted gray line are close to each other, which serves as good validation because we held out the UK solid gray line and saw whether we could recreate it. And here you see, though, that the dotted blue line and the dotted green line are further away from each other than was true for the US. And that kind of shows you the heterogeneity that is true across different countries, because these different countries react differently to the same intervention. Then we again did this for the various countries that did different things post-COVID. For example, Brazil and Turkey enacted a moderate mobility restriction. And again, pleasingly, the solid blue line and the dotted blue line are relatively close to each other. And then we have a synthetic Brazil under low mobility restriction and a synthetic Brazil under the green mobility restriction. And so same thing for Turkey. And again, we did the same thing for countries that had enacted a high mobility restriction post-COVID, so such as India and Ireland. And we see that the dotted green line and the solid green line are again close to each other. And you can see the counterfactual India under the various interventions, and same for Ireland. And so the key takeaway for this part is that if you believe the SI estimate, it enables personalized policy or program evaluation with multiple treatments. So now I'll actually go through the synthetic interventions estimator, and afterwards I'll explain when and why it works. So the key intuition for the SI estimator is that if you want to estimate, let's say for the US, what happens to it under the green intervention, you somehow want to leverage data for the other countries that actually went through the intervention of interest. Now, the problem is all these various countries are heterogeneous, and that is why you require all the units to be under the same intervention for some number of measurements. And that having that common amount of common measurements under the same intervention is what helps us deal with the unit heterogeneity. So the inspiration for synthetic interventions really comes from synthetic controls, which is now an incredibly popular method and generally a field of study within econometrics. This was invented by Alberto Abadi and his co-authors and through a variety of papers, and it served as, at least for me and Dennis, a major source of inspiration for this work. The key goal in synthetic controls is to estimate counterfactuals in the absence of interventions, in particular under control. So for example, you could ask, say Brazil, which did intervene and did do something post-COVID, what would have happened to Brazil had it remained under low post-COVID-19? The basic idea is we're going to learn a model under control. So Z pre represents the data of the countries that remained under control post COVID-19 breaking out, their pre-intervention data. So I'm going to call that Z pre. Y pre represents Brazil's pre-intervention data or pre-COVID-19 breakout data. What you're going to do is to learn a linear model between Y pre and Z pre, and the linear model is going to be called W hat. It's going to be regularized to lie within some space capital W, and I'll talk about that in a second. Now what you're going to do is you're going to look at the post-event intervention data of the countries that remain under control. We're going to call that data Z post. We're going to take Z post and the learned linear model W hat, apply them together, and that gives you an estimate of the post-intervention data for Brazil had it remained under control. It's a beautifully simple method, and that's why it's gained so much traction especially in applied econometrics, is because you can apply this. You can see there are many different applications for it. Now, this W hat is what we call a synthetic control, and now how do you regularize the linear fit? So Badi and his co-authors recommended W being the simplex. So what that means is that the linear fit you have is going to be a non-negative and going to sum to 1. And this has a variety of very attractive properties. For example, one is you only interpolate. So you do not go outside the observed outcomes of all the countries that remain under control. Secondly, it has this nice interpretation because you can say, for example, that Brazil is 20% the US, 50% the UK, 30% Italy, for example. So it has this nice interpretation as well. And also it actually, by forcing W hat to lie within the simplex, it enforces sparsity in the learned model. So most of the coefficients will be 0. And if you want to have a overview of synthetic controls and the state of the art of it, Alberto has written a nice review of it in 2020, and the citation is at the bottom of the slide. Now, towards synthetic interventions, the goal in synthetic interventions is to estimate counterfactual both in the absence and the presence of interventions. So, example, we can ask the question of what if the US had enacted the moderate policy post COVID-19 breaking out? So the idea is going to be similar. We're going to learn a model under control. Similarly here, now Z pre is going to represent the pre-intervention data of the countries that go under moderate mobility restriction and the post COVID-19 breaking out. So we look at the countries that go under the blue intervention and the post-intervention, look at the pre-intervention data, and that's going to be called Z pre. Y pre represents the pre-intervention data of the US. We learn a linear model between Y pre and Z pre, call that W hat. Now we look at the post-intervention data of the US, and we're going to call, of the countries that went under the blue intervention. We're going to call that Z post. We're going to take Z post and W hat, multiply them together, and that gives you the counterfactual for the US under moderate mobility restriction. And that's exactly what we did to produce the synthetic trajectories of the US under the gray, blue, and green in the preceding section. Now, let's say you want to find out what happens to the US under high. Again, you repeat the same process, except now the difference is you look at the data of the countries that go through the green intervention or high intervention, whatever you want to call it, in the post-intervention period. Right? So if you want to decide different interventions, you're simply picking out the right donor group. And the way you pick out the right donor group is by looking at what they do in the post-intervention period. And we call this W hat a synthetic intervention. So in these previous works, we saw that they restrict capital W to be the simplex. In our case, we propose that we restrict W to lie within the space, the linear space spanned by the first k singular vectors of Z pre, where k is a hyperparameter. So it's a linear constraint that we put on the model learned. And I'll talk about in a second why this is a good idea. But you can see that restricting W to lie within the first top k singular vectors of Z pre could equivalently be thought of as principal component regression. So that means is you first do PCA on Z pre, take a low rank approximation of it, and then learn a linear model on top of it. And that's an equivalent formulation for what we're doing. So why a principal component regression, or PCR, rather than a convex regression? So as you can see, one benefit of learning, of doing PCR is that you're not restricting W hat. So it's allowed to be a linear model. And versus if you do convex regression, or more recently, some people have also been thinking about doing lasso, that restricts the W hat learned to be sparse. Now, a linear model is obviously more expressive, but the problem is you might have overfitting, especially if you have lots of donors or lots of units that you're running this regression over. So the question is, how do you prevent overfitting? Well, what we do is you want to exploit the low-rank structure that exists in Z-pre. So by doing PCA on Z-pre, what you're really doing is you're enforcing spectral sparsity in Z-pre. Right? So instead of enforcing sparsity in W hat, you now enforce sparsity in the singular, in the spectral sense over the singular values of Z-pre. And some additional benefits of doing so is that it becomes robust to noise and missing values. So if you look at the data on the figure on the top right, here is a plot of the singular values of some of the data that we just talked about. So you can see there are a few singular values that are very large, and most singular values are really small. And so what we call those first few singular values to be the signal, and the remaining singular values to be noise. And you can see as we add more and more noise to the data, the noise is spectrally diffuse. So in some sense, it doesn't really perturb the first few singular values, and it affects all the singular values in an equal way. And that's why by thresholding, you're kind of cutting out this additional noise in the data, and it's becoming robust to noise and missing values. And this general field is called errant variables regression. For more details on why PCR is a good idea, there are a couple of papers that me and my co-authors wrote, and the citation for that is on the bottom right of the slide. And the good thing about doing PCA is that you can verify whether this low-rank structure exists in practice. You can always plot the spectrum of Z-pre, see whether it's low rank. If it is, then apply principal component regression. If it isn't, then don't apply it. And this is good versus say something like lasso or convex. You have to assume that the model itself is sparse, which may or may not be true and is harder to verify in practice. Lastly, I'll say in terms of algorithmic fine print, if you have covariates that you want to add to your fit, we talk about how one can do so in the paper itself. And now, lastly, I'll go to the causal framework of when and why SI works before handing it off to Dennis to talk about the theoretical results. So one thing that maybe is making you uncomfortable is that we learned this model under control, and then we applied it to make a prediction under intervention. So we learned a model under one interventional regime and applied it under a different interventional regime. So you can ask the question of when can you learn a linear model and transfer it between different interventions despite this missing non-random data or despite latent confounding. And what I hope to convince you by the end of the section is that it is possible under a few key assumptions. So the first assumption we make is what we call the tensor factor model. So first, to back up, a lot of times in the panel data literature or the interactive fixed effects literature in econometrics, to impose structure across units and time, we assume that the data is low rank. So for example, in synthetic controls, you assume that the data associated with control it has a low rank representation. Here R represents the rank of this matrix, and then U and V represents the latent unit time factors and the latent unit factors and the latent time factors. Now, if you want to add structure not just across units and time, because we want to actually make estimations for different interventions, not just in the control, we need to add structure across interventions as well. And so now what we say is that there's a low rank tensor, and there's a latent factor associated with intervention as well. Okay, so, and this R now represents what we call the CP rank of a tensor, and that's a well-defined quantity. Now, to actually define the potential outcomes, which are a stochastic quantity, we say that at the sum of this, so let's say YNTD represents the potential outcome of unit N at time T under intervention D. We're going to say that that can be written as the expected as the sum of the latent factors given by UN, BT, and SD, which are latent factors for unit N, for time T, and intervention D, plus a residual term given by epsilon NT. So epsilon NT represents the residual that's not captured by the latent factors, right? So the latent factors represent, in some sense, the expected potential outcomes, and the epsilon NT represents the remaining residual. So that's the first as key assumption we make, is that this tensor factor model exists over the expected potential outcomes. The second assumption we make is what we call linear span inclusion, which simply means that for unit N, let's say that's our target unit that we want to produce counterfactuals for, it has this particular structure, what we call linear span inclusion. So let ID represent the subgroup of units that received intervention D. And what we're going to say is that the latent factor associated with unit N lies within the linear span of the units that go through intervention D. So J are the units that go through intervention D. Let's look at all of their latent factors, and I want unit N's latent factor to lie within the linear span of these particular latent factors. Now, if your data is low rank, then you can easily see that this condition is really quite minor and almost always holds. So now I'm going to build, this is the only math we're going to do here, so I apologize in advance. So what does this buy you, this linear span inclusion in the tensor factor model? So let's look at the expected potential outcome of unit N at time t under intervention D prime. So by the tensor factor model, we have the following representation of it, that it has this low rank factor representation by UNL, VTL, and SD prime L for any TD prime. And this holds by the tensor factor model, assumption 1. Then by the linear span inclusion, which is assumption 2, we can write the latent factor for unit N as a linear sum of the latent factors that for the units that go through intervention D. Then again, by the tensor factor model, we have that Y and TD prime can be written as a linear sum of the expected potential outcomes of the units J at that same time T under intervention D prime. And the linear model, which represents the linear span inclusion, W and D, is invariant across time and interventions. And so it's really the linear span inclusion in the tensor factor model that lets you learn a model under control and apply that same linear model under intervention. Right, and this is indeed why asymptotic intervention and also asymptotic control exists. Now, lastly, what kind of confounding is allowed? I'm going to give you a causal DAG perspective on this. So here in this causal DAG, LF represents all the latent factors. For example, all the collection of UNs, VTs, and STs. D is a random variable which represents all the intervention assignments to all the various units. Now, what we need is that the potential outcome yn1D, for example, is given the parametric form, can be written as some function of the latent factors and the residual epsilon n1. Now, the key causal assumption we make is that the intervention assignment does not have a direct effect on the residual term epsilon n1. Okay, so that key arrow is missing. And that's really the key causal assumption we're making, is that conditional on the latent factors, the remaining randomness in the potential outcomes is independent of treatment. Now, what that means is that given this tensor factor model of the potential outcomes, plus the assumption that conditional on the latent factors, the intervention assignment D, and the residuals are independent, that essentially implies that the interventions are independent of the potential outcomes conditional on the latent factors. Right, so this is what we call assumption A3, which is selection on latent factors. And this can be thought of as an analogous to selection observables, except now they're latent factors rather than observed covariates. So just to build some intuition from, say, the COVID-19 example, here UN could represent things like, say, population demographics, the healthcare system. It could also represent things that are just not available from data, say the cultural leanings of that country. VT, for example, could represent the number of days since COVID-19 began. It could also represent things like, say, the global political trends. And SD, which is a latent factor associated with the intervention, could represent how the transmission rate of COVID is a function of the mobility restriction, right, which may or may not be available. And clearly you see here that the intervention assignment D is not independent of the potential outcome, right? Because the number of elderly people in the US is going to affect both the mobility restricting policy that you put in place and the number of COVID-19 deaths. But the hope is that the latent factors are rich enough that conditional on them, the potential outcomes and the treatment assignments become independent. So what we set out to ask in this section is, when can we transfer a linear model between different interventions despite latent confounding? The three key assumptions we're going to make is the existence of a tensor factor model across the units, time, and interventions. Second is this linear span inclusion for the target units latent factor and the donor units, the received intervention D. And lastly, the selection and latent factors assumption, which is the intervention assignments are independent of potential outcomes, conditional latent factors. Now, in the next section, Dennis is going to take us through the key theoretical results given these collection of assumptions. So I'll pass it on to Dennis. Thank you again for your time.
Thanks, Anish, and thanks again to everyone for being here. My name is Dennis, and I'll be your tour guide for the remainder of this talk. So in what follows, I'm going to first formally define our causal estimate of interest. Then we're going to show that this philosophical quantity can indeed be identified through observable quantities. I'll then present the statistical guarantees of our estimator and then cap off our conversation with one or two real-world case studies depending on the time. So with that said, we'll dive into the definition of our causal estimate. So thanks. Towards this, we will, without loss of generality, just consider a particular unit n and intervention d pair. So we're going to represent this pictorially by the first row in the blue color in the tensor you see to your left. So in words, we're going to define our causal estimate, represented by theta nd, as unit n's expected potential outcomes under intervention d averaged over the post-intervention period and conditioned on its latent factors. Pictorially, this would just be the average over all entries you see in the highlighted blue box. And indeed, the key causal challenge in estimating theta, and in essence, the fundamental problem of causal inference, is that, as Anish had alluded to earlier, is that we will likely only ever observe unit n under one of the d interventions, yet want to produce counterfactuals for unit n under all possible d interventions. So under our causal assumptions, namely tensor factor model, linear span inclusion, and selection on latent factors, we established that we can express our causal estimate theta nd for any nd pair as a function of empirical quantities. So more specifically, theta nd can be written as a linear combination of the expected observed outcomes associated with those units that receive intervention d, averaged over the post-intervention period, where the conditioning is now both on the latent factors LF and the treatment assignments d. As such, the name of the game in estimating theta is to then first estimate the model parameter w of linear weights, which is going to be specific to the target unit n and defined over the subgroup of units that receive the target intervention d in the post-intervention period. So if we return to our COVID example, this really is just implying that we can predict the US's mortality rate under moderate mobility in blue by taking a linear combination defined by W of the mortality rates for those countries that did enforce the moderate mobility. In practice, however, it is unlikely that we're ever going to know W precisely. In fact, we may be learning W from limited measurements under a single interventional framework, for instance, a small pre-intervention period under control. Therefore, the question we tackle next is to understand the conditions that allow for faithful recovery of W so that we can make inferences beyond the pre-intervention period. And so in the language of statistics and machine learning, we often refer to this as generalization from your in-sample training to your out-of-sample testing data. To this end, we establish a sufficient condition that guarantees successful counterfactual estimation. Intuitively, this condition is really requiring that the complexity of your post-intervention data, denoted by Z post, used for prediction, is at most as complex as the pre-intervention data Z pre used for learning. So more specifically, we're going to define complexity by the subspace spanned by the pre and post-intervention donor matrices. And to gain a little stronger intuition for this notion, let's let U pre and U post denote the left singular vectors of Z pre and Z post respectively. In words, the rows of these two matrices are going to represent the latent factors associated with the donor units that received intervention D during the post-intervention period. And thus the dimension of your latent space is characterized by the rank of the respective matrices. As such, we're going to require the subspace spanned by U post to lie within that of U pre. In light of this, we're going to henceforth refer to this condition as subspace inclusion. Now, I want to note that this is a purely linear algebraic statement. In contrast, standard generalization analyses typically make distributional assumptions. For instance, a very common one is that the pre and post-intervention samples, which correspond to your train and test samples, are drawn IID. In the SI framework, however, such an assumption may be unrealistic since potential outcomes from different interventions are likely to arise from different distributions. For instance, in a clinical trial, the health response of a patient under placebo is likely to follow a distribution under a well-designed drug. And so without going into too much details, I just finished by remarking that this condition may also have potential implications towards transfer learning, learning with covariate shift, and causal transportability, all of which models are learned under one domain and then transferred to another. As an important intermediary result, we note that if subspace inclusion holds in addition to the other causal assumptions, then we can actually rewrite our identification result. In particular, we can replace the model parameter W, of which infinitely many of such exist in high dimensional settings where the number of units far exceeds the number of measurements, with the projection of any solution W onto the subspace spanned by U pre, which we'll denote as W tilde. And note that by definition, this also corresponds to the unique minimum norm solution within U pre. So in words, this really means that if I want to make inferences for unit N under intervention D, then I don't necessarily need to learn W entirely. Instead, under subspace inclusion, I actually only need to learn the component of W that lives within the span of my pre-intervention U pre. So now that we're fully armed with all of our key operating assumptions, we're going to now present our statistical guarantees. However, in the interest of keeping things as clean and simple as possible, and so as to not distract from punchlines, I'm going to hide away some of the details, such as our additional assumptions on sub-Gaussian noise or Sitwell, and instead invite the interested listener to see the paper for the full formal statement. So the first result that we have is one on model estimation. In particular, we established that PCR is a consistent estimator of this unique minimum norm solution W utility. That is, the L2 error scales with the minimum of the square root of T naught, which represents the number of pre-intervention points or the size of our training data, and ND, which is the number of donor units that we have. Below, we're going to consider a simulation analyzing the parameter estimation of PCR with respect to the minimum norm solution to the left and a random solution to the right across varying data sizes. And as we see, the parameter estimation error with respect to the minimum norm solution decays as the sample size increases, but remains stagnant with respect to a random solution. And so this highlights that PCR performs implicit regularization by recovering this minimum norm solution amongst all feasible solutions. Next, we established that the SI estimator yields a consistent estimate of our causal estimate of interest theta ND for any ND pair, in that the estimation error decays as the parameters T naught, T1, and ND increase. And here T1 is going to represent the number of post-intervention measurements. And similar to the previous slide, we also designed a simulation to reinforce our theoretical findings. Anish, do you mind clicking? Yes. So here we plot the absolute counterfactual estimation error as the post-intervention period T1 increases. So as the plot suggests, the error shown in blue gradually decays to 0. And in fact, given our choice of T naught and ND, the other parameters, we see that the simulated decay rate here matches the theoretical rate of 1 over square root T1 shown in black. Finally, we proved that the error between our estimate and the true causal estimate, once normalized by square root T1 over sigma, which is the noise variance, and the L2 norm of the minimum norm W, converges in distribution to a standard norm. In turn, this then allows us to construct confidence intervals. For instance, we can compute a 95% confidence interval using the expression you see on the screen, where very importantly, the quantities within our intervals are not only tractable, but also come with provable guarantees, the details of which can also be found in the manuscript. Okay, so in order to really drive home the importance of subspace inclusion, I'm now going to discuss two illustrative simulations. So for the first simulation, our objective is to recover the underlying causal estimate under two different scenarios. So in scenario 1, shown on your left, the pre and post intervention potential outcomes are going to obey the same distribution. And so this may reflect the standard panel data or synthetic control setting one may encounter, where the aim is to estimate the average potential outcome under control for a treated unit. In scenario 2, shown on the right, the pre and post intervention potential outcomes are now going to obey different distributions. So this may now reflect the opposite situation where you may want to estimate the average potential outcome under treatment for a control unit. In both settings, however, subspace inclusion is going to be enforced. Additionally, we're going to allow the two settings to share identical pre-intervention data and really only differ in their post-intervention data. As such, the same linear model is going to be learned in both settings. Nevertheless, we're going to use this single linear model under two different interventional frameworks. One in which the post-intervention outcomes are drawn from the same distribution as the pre-intervention potential outcomes on the left, and the other on the right in which the two sets are going to follow different distributions. And what we find is shown on the plot you see on the screen, where the theoretical normal distribution around the true causal estimate is shown in black, while the histogram of estimates as per our SI algorithm is shown in blue. And again, just to reemphasize, because the post-intervention data differ in the two scenarios, we have two causal estimates. So it's about minus 3.6 to the left and minus 1.5 to the right. And as our theory suggests, our result tells two narratives. The first is our estimates are normally distributed around the true causal estimate. And the second is that these estimates remain normally distributed even when the pre and post intervention potential outcomes follow different distributions. So in summary, this simulation really supports our causal framework, as it shows that it is indeed feasible to learn a model under one intervention setting and then transfer it to another one, even if they obey different distributions. So in our second simulation, we're now going to violate subspace inclusion. However, we're going to allow the pre and post-intervention potential outcomes to be drawn IID. And unlike the two plots from the previous slide, we now find that our estimates are not well approximated by normal distribution anymore, centered around the true causal estimate. And the juxtaposition of these experiments really reinforces the importance of subspace inclusion for successful counterfactual estimation. And additionally, we also just want to note that we hope that these studies may also be of independent interest to those in the statistical learning community, since standard generalization techniques often rely heavily on IID assumptions, and to the best of our knowledge, subspace-like inclusion principles have not really been explored. So in light of our revealing simulations, I'm now going to describe a data-driven hypothesis test to check when subspace inclusion holds in practice. And to gain an intuition for this test, let's consider the following two hypotheses. So our null hypothesis H0 is that the span of U post is contained within that of U pre, and our alternative hypothesis H1 is that it's not fully contained. Now, if I condition on H0, it follows that U post is going to be orthogonal to the orthogonal complement of U pre, represented by the identity matrix I minus U pre transpose. Hence, the size of this projection is going to be exactly 0. In contrast, if H1 holds, then this value is going to be strictly positive. Therefore, the size of the projection serves as a very natural test statistic. Of course, we're never going to fully observe U pre and U post perfectly due to the stochasticity of our observations induced by the epsilons. Therefore, as Anish had presented in the algorithm section, we're going to use the top principal components of the observed donor matrices Z pre and Z post as proxies, which we're going to denote as U pre hat and U post hat. And so this yields the following test. For any significance level alpha, we're going to retain our null hypothesis if tau hat is less than or equal to some critical value tau of alpha. And we're going to reject our null hypothesis otherwise. And again, to build some intuition, just note that in the ideal setting where U pre and U post are perfectly observed, tau of alpha is going to be exactly 0. And using our choice statistic, we can then control both the type 1 and type 2 errors. That is, for any significance value alpha, both errors occur with probability at most alpha, and our critical value vanishes with increasing data. And before I move on to the empirics, I just want to briefly mention that the exact constants of this tau can be found in the paper, as well as two other notes on how to compute it. One is an exact computation, and the other is a complementary practical heuristic. All right, so this really wraps up the primary aspects, theoretical aspects of our work. And so next we'll continue our journey by analyzing a real-world case study. But before I go into that, I'd just like to take a quick step back again and just recall one of our earlier primary goals. In particular, let's consider the setting where we have N units and D interventions. Now, in many real-world applications, randomized control trials, or RCTs more compactly, are considered the gold standard mechanism to draw causal conclusions, unless they're heavily used in practice. In general, RCTs only require N experiments, which is sample efficient, but they typically only prescribe one intervention across all units, and that's the one that corresponds to the best average treatment effect. In contrast, if we consider what we coin as an ideal RCT, where each unit is exposed to all D interventions, then we're going to know precisely the best intervention for every unit, thus achieving a high level of personalization. But this then comes at a cost of N times D experiments, which can be infeasible in many settings. So as we transition from the left to the right, personalization increases but at the expense of feasibility. And so this begs the question, can we design a framework that achieves the personalization of an ideal RCT, yet retain the feasibility of standard RCTs? Towards this challenge, we discuss a case study that emerged from a collaboration with the e-commerce platform that conducted a large-scale A/B test to match the right incentives to the right customer group in order to increase engagement overall. More specifically, in this experiment, the company partitioned its customers into 25 groups with over 10,000 customers per group, based on their historical expenditures, characteristics, etc. Additionally, the company considered 3 interventions corresponding to discounts of 10, 30, and 50%, as well as a control where the customers had to pay the standard fee. And then the customer engagement levels were then collected over 8 days. And because of the large number of users within every subgroup, the company then randomly partitioned the users within every single one of the 25 groups into 4 further subgroups, where each of the subgroups then received one of the 3 discounts or control. And so from our perspective, this setup is perfect because this data set effectively provides us access to the customer engagement levels for all user groups and all intervention pairs. In other words, we have access to the entire,
Sorry to interrupt. I just want to remind you of the time you have. Could you wrap up in like 3 minutes or so?
Yeah, I'll just wrap up at the end of this case study.
Thank you.
So in other words, we have access to the entire ground truth tensor of potential outcomes. And so this case study really allows us to properly assess our framework and algorithm, specifically to address the challenges laid out in the previous slides. And so hence, to simulate a data efficient trial, what we're going to do is we're going to hold out part of this tensor as a test set. In particular, we're going to retain the controlled data across all 25 groups. But for every one of the groups, we're only going to have access to their engagement levels under one of the 3 discounts. And so this induces the following block sparse tensor. So in short, our objective is to recover the underlying tensor on the left from the sparse observation set on the right that reflects a more standard A/B testing setting. And to quantify the utility of our approach, we're going to use the following modified R-squared statistic, where the numerator is going to represent our squared error associated with the SI algorithm, and the denominator represents the squared error associated with the RCT estimator, which is really just going to take the average outcome across all the customers that received discount D. So if the customers were homogeneous, then the RCT estimator will be a good predictor of the causal estimate. So as a result, the denominator is going to be small and the overall squared error will be small as well. In effect, this metric captures the gain by personalizing prediction to your target customer group and intervention. And so the more positive this value is and the closer it is to 1, the more utility is to be gained from personalization. So in the interest of time, I'm going to skip over the verifying causal assumptions and say it is verified and just jump straight to the results instead. So in the middle column of our table, we're going to first show our hypothesis test results, which passes for all discounts at a significance level of 0.05. In addition, across all discounts and over multiple iterations of the synthetic A/B testing setup described previously, we achieve an average modified R-squared of 0.98 and a standard deviation of at most 0.04, which is shown in the rightmost column of the table. So in words, these results are really just showing that the SI algorithm is far outperforming the RCT algorithm, which indicates that there is significant heterogeneity amongst the user groups and how they responded to the promotions. And this warrants the e-commerce company in running separate A/B tests for each of the groups, which actually required a significant engineering effort on their part to implement and costed a sizable amount of money. And so this leads us to the second and more important takeaway, which is that this experiment showcases how SI can enable what we call data efficient trials, as the synthetic A/B testing framework only required 50 experiments, so 1 control and 1 discount for each of the 25 customer groups, compared to the actual A/B testing framework, which required all 100 experiments, so 1 control and all 3 discounts for each of the 25 groups. And more generally, SI only requires each unit to undergo at most 2 interventions, independent of the number of interventions D, as compared to the D times N experiments needed in what we call an ideal A/B testing scenario. And as previously aforementioned, this becomes more and more significant as the number of interventions or the level of personalization grows. And so I'll skip over this next case study and then just jump straight to the summary of this work, and just say that as a very quick summary, in the very beginning, we presented a causal framework that reinterpreted the language of potential outcomes through the lens of tensors. And this perspective is really what enabled us to learn and predict under different interventions at a unit by unit granularity, despite the presence of latent confounding. We then armed this framework with an algorithm that is robust to noise, offers more predictive juice, and is also not very data hungry. Additionally, we provided statistical guarantees for this algorithm and showed how to produce confidence intervals and how to furnish a hypothesis, how we use a hypothesis test to verify when the algorithm can be safely applied in practice. And finally, we discussed one real-world case study on how to enable data-efficient trials using synthetic A/B testing. So I just want to thank everyone again for coming to this talk. Feel free to contact either myself, Anish, or Devrat on the emails there. And also just want to send a big shout out to Alberto Abadi, Abdullah Alamar, Romain Cousin, Esther Duflo, Anna Makusheva, and Rohit Singh for their invaluable help and fervent support. Thank you.
Thank you. Thank you, Dennis and Anish, for the great talk. I think we have time for one question. So we have a question by Richard Burke. I am unmuting now, Richard.
Yeah, this looks a lot like meta-analysis. And a common problem with that is that interventions which have the same name aren't really the same. And so I wonder, don't you have to assume that the content of the intervention across countries, let's say lockdown, is identical regardless of the country that uses that name. I didn't see that in your assumptions, but maybe I missed it, or maybe I just don't understand.
Yeah, thanks for your question, Richard. I think that totally makes sense. So one assumption that we did not talk about is SUTVA. It simply says that the observation you're getting is exactly the potential outcome under that particular intervention. And so, for example, in the COVID study, what we're saying is that what you're observing is the outcome for, let's say, the US, where they had a 5% drop in mobility compared to their baseline, or for Brazil, a 20 to 35% drop in mobility compared to their baseline. And that's how we're defining the intervention.
But you don't know what the content of it is.
So, sorry, could you expand on that a bit more?
Yeah, I mean, something happened in the United States, and something happened, let's say, in Canada, but you don't know what that something is. All you know is that it's called, for example, lockdown. But lockdown in Canada is different from a lockdown in Brazil.
Oh, absolutely. Yeah. So I think in this case, we are defining it simply in a data-driven way, which is by the drop in mobility that was actually measured by, in this case, Google compared to the baseline. So we're not calling it a medium lockdown, a high lockdown, but we're defining it in terms of that particular Google mobility report, which says it's a 5% drop from their baseline, from the data that they're collecting on mobile phones of all their Google users throughout that country. So that's the way we're defining it. Dennis, if you want to add something.
Yeah, so I think that's a great question. And I think it's something that we put a lot of thought into, because you're completely right. Different countries implemented different policies, and what one place calls a severe lockdown is different from another. But what we saw is that a lot of these different kind of policies that were put into place were really trying to limit mobility. And so we're really using mobility as kind of like a proxy instead, and saying that, we don't really care about what the actual policy that you implemented is. We're really just going to look at how did that affect mobility in the very end. And as Anish said, that we use Google's mobility reports to kind of see the difference in drops after COVID kind of really took off compared to what their national baseline was before COVID took off.
All right, thanks. Georgia?
Thank you, Anish and Dennis, for your presentation. We are now ready to switch over to discussion. If you're ready, Jason.
Okay, so thank you, Anish and Dennis, for this excellent talk and this paper that I think does contributes a lot to the synthetic control literature and the causal panel data literature. So I think there are three major contributions here. One is that the paper extends this latent factor model to the multiple treatment setting. And this is important because current estimators are squarely focused on estimating potential outcomes under control for either a single or multiple units responding to one treatment. But as the authors point out, we are always interested in situations where there might be multiple different treatments. In the paper, they discuss, there's a section on a connection to tensor estimation, where we could think of potential outcomes as a order 3 tensor, where each entry is a time unit or treatment potential outcome. And this is like a very natural fit for this type of estimating potential outcomes. We can think of it as a matrix or a tensor completion problem. So I think that's an exciting development. And then lastly, the authors do a really good job connecting the synthetic control literature to machine learning literature. And one of these connections is that the idea of counterfactual estimation under distribution shift. So in the standard synthetic control literature, we typically assume that the training and test sets, so the distributions of the control units and the treated units under potential outcomes under control are drawn from a similar distribution. But in this synthetic interventions framework, we can have different treatments sampled from different distributions. And that is because we have these latent time and treatment factors that can be differently sampled. So that's an important contribution. And so there's a few things I want to point out with the latent factor model. So the potential outcomes here is a function of these latent factors, so the time and treatment specific coefficients, and then latent factor loading, so the unit specific intercepts, plus this random noise. And so, so I think one important thing to point out is that the rank R here, so the rank is the number of non-zero singular values that are recovered from a SVD of this product. In the latent factor model, typically we just fix the rank R, so we just assume that we know what R is. In the matrix completion literature, which I'll discuss later, we're typically only assuming that this this matrix here is low rank. And so my reading of this paper is that the authors are kind of blending the fixed latent factors models and the matrix completion models, and assuming that that the rank is both fixed and low rank. Another thing I want to point out is so they make the exogeneity assumption that the errors are independent of treatment assignment, conditional on these latent factors and loadings. And this sounds kind of weird because so we don't observe the latent factors and loading, they're latent. And I just want to point out a similar assumption is made in this paper by Zhu in 2017, where he extends a IPE model to synthetic control. And so there the conditioning set includes the latent factors and loadings and the covariates. And this is kind of also similar to unconfounded assumptions in semi-parametric difference estimators. And in that case, the conditioning set includes fixed effects, which are meant to capture unmeasured confounding. So I think there's some precedent to this assumption. And I think the authors could maybe make more clear that there's some precedent. So I just want to compare past approaches with this approach. My reading is that the synthetic interventions framework is kind of a blend of the two, but borrows more from the interactive fixed effects models. So I mentioned the paper by Zhu, which kind of borrows from this earlier paper by Bai. And in this framework, they assume the matrix has a low rank, the matrix has a fixed rank, and there's an implicit regularization happening through choosing the rank. In the synthetic interventions approach, where typically they're assuming fixed rank and a low rank matrix, and they're also making this additional assumption on the smallest non-zero singular value. And so one thing that I also want to point out is in comparison to the matrix completion approach, they're not fixing the matrix, the size of the rank. They're just assuming that the matrix is low rank. So just to offer some final thoughts, I think the paper does a really good job in verifying the assumptions that are made through simulations and empirical work. There's a lot of assumptions in this paper. So it's really important to point out when the assumptions are met and when they are failed. And as the authors point out, in all the cases, these assumptions are met in the simulations and empirical application. So one question is it possible to extend this framework to handle continuous treatments? So we just assume that the treatments D are a discrete number of treatments, but can they be continuous valued? this would be like really interesting, for instance, in evaluating the efficacy of drugs. So drugs could take a continuous value. Another question is, how do we incorporate a treatment model into this approach? So in the paper by Athey et al., the matrix completion paper, they propose, for instance, weighting the training loss by the inverse propensity score weights of the controls, trying to correct for any distributional imbalances. And so the IPW weights are estimated using a treatment model. So I was wondering if maybe this framework could do something similarly. In the paper, they do mention the idea of extending the method to a staggered treatment scenario. So I think that is also really important. I think that's a direction that most of these synthetic control estimators are going in. So I think currently, like, not being able to handle varying treatment times is a key limitation of the paper. And lastly, I want to point out that there are connections made to the synthetic control and econometrics literature and the RCT literature, but there's also this potential connection to make to the optimal treatment regimes literature. And so in this literature, they're trying to find what the optimal treatment is for each individual corresponding to this individual's covariance. And so there's an idea of optimality that the treatment regime would lead to the best outcome on average. And so finally, my question would be, in the synthetic interventions framework, we're considering estimating counterfactuals without covariates. Is there a way to personalize treatment, or what is the way that we can decide what the optimal or treatment is for an individual? Thank you.
We're running out of time, but Anish and Dennis, if you want to have a couple minutes to respond.
So firstly, Jason, thank you very much for the thoughtful feedback. I think I very much agree with most things or everything you say. I think the point of covariates in continuous treatments, I think, is a really good one. And I think one way to get to continuous treatments is possibly by covariates. So say you had covariate data about an intervention. For example, in medicine, some covariates about the chemical compounds or the dosage levels, then you could use that information now to build a counterfactual for a particular unit under a dosage that has not been seen by anyone. So covariates could be one way of doing that. And similarly, covariates about the units could help answer the question of the counterfactual for a unit for which you observe no data. So covariates could be a good way of personalizing to things that are just, you have no data about at all that can be captured by this particular tensor. So I think that's a really good point. And I think another use of covariates is, as you said, is possibly to make the identification argument more believable, because you said there's latent factors and we assume exogeneity based on latent factors, but maybe there's only exogeneity based on the latent factors and the covariates together. And so you want to regress on both of them in some sense. And so we talk about that in the paper, and yeah, so I just wanted to agree with you there, and thank you for the references.
Yeah, I also just wanted to thank you, Jason. I think this was extremely helpful and really appreciate you doing this. And Anish is a lot more eloquent than me, so I think he already said everything very well. But also thank you to the references. I think we definitely do a better job in our next iteration of putting in those other citations as well. Thank you.
All right, thank you both, Anish and Danish, for the great presentation, and Jason for the discussion. Next week, we have another one of our PhD days. We will have two presenters. The first one will be Maggie Makar from MIT, and the second one will be Xiaoji Mao from Cornell. We look forward to seeing you there.
Thank you again.
Thank you.
Thank you.